Hello, Chemistry 10HH students. This is Mrs. Altman. We are on video number 40, gases part 6. This is the last video in chapter 5. Here are our objectives for today's video. Pause here. So last video, we talked about kinetic molecular theory and why some gases would be more ideal or less ideal. And today we're going to focus on real gases, meaning things that are not 100% ideal. So we're going to see that they are not so small that the volume is negligible and that they do experience intermolecular attractions. And we are going to need to correct PV equals nRT to account for this. Pause here. So what is presented in front of you is just modified PV equals nRT. So OBS, that is for observed. So that would be something that you would actually see in a lab. Every single gas has values of A and B, most of which you can look up in your textbook. A is just a constant with appropriate units. B is a constant with appropriate units. And typically, we're going to be taking this equation here and solving for observed pressure. But before we do so, let's boil down where we got A and B from and how they actually change things. Pause here. So the first correction factor, which is B, is correcting for the fact that some gas molecules have very large atoms or molecules associated with them. So what that's going to do is that's going to take away from that empty space, our V. Our V is actually accounting for empty space. And then we subtract off NB, the number of moles times this constant B. That gives us a smaller observed volume. So what we'll see is that when we have really, really big gas molecules, our observed pressure is going to be higher than we would have predicted from PV equals nRT. Pause here. So what I said towards the end of the last slide really helped to answer it, but I'll explain it in a different way. So higher values of B just means that I have a larger gas particle, whether it's an atom or a molecule. So imagine that if you had a bucket and you were pouring water into it, you would be able to fit less water in if you were to decide to stick a bunch of baseballs into that bucket. It's the same idea here. You're going to be decreasing what I like to call the effective volume or the observed volume, and then there's that indirect relationship between pressure and volume. Pause here. So then our second correction factor is accounting for intermolecular forces. So that is what A accounts for. So the higher values of A that you'll see, for example, with water, account for the fact that you're going to have really high intermolecular forces. This is going to decrease your observed pressure. The reason why is because if you have high intermolecular forces, instead of particles bouncing randomly off of one another as they would if they were completely ideal, they'll interact with one another inside of the container. And that is going to prevent gas particles from hitting the walls of the container, which will decrease the pressure. Pause here. All right, so I'm going to work through this. So first, you're going to want to rearrange it for P odds, or observed pressure. And then you're going to start plugging things in, which is going to get to be a little annoying in terms of sig figs. You don't typically give a whole lot of these on an assessment. For questions like this, I'm just going to really highly suggest you go through these slowly and methodically to make sure that your sig figs all check out. For A and for B, you can consider these as not impacting sig figs. Since we are going back and forth between multiplication and addition subtraction, it's important that you do these in separate steps. And even when I am doing these problems, I still list them out in separate steps. And then some of you are probably sitting here thinking, wouldn't I get the same thing if I did PV equals nRT and just forgot about the A and the B? And in this particular case, you would be absolutely correct. There are cases where you will get the same answer, whether you use PV equals nRT or whether you use the van der Waals equation. And then there are cases where you get a slight difference. You're never going to see a difference of more than, I think the highest I've ever seen in a problem in your book is like maybe 5% at the very highest, but certainly nothing higher than that. And usually you get the same answer either way. If you get the same answer either way, that tells you that your gas is pretty close to being ideal. Neon is a fairly small gas and it doesn't have very high intermolecular forces, so that makes sense. Pause here. So I said this in the last video, but I included it here because I think it's something that's really, really important to understand. So the answer is high temperatures. There's a couple of different ways that you could think about this. At high temperatures, mathematically, the impact of B is going to be less, and also the impact of A. So that's one way you can think about it. Or the way that I think about it is at higher temperatures, things are moving faster, which is the opposite of a liquid. So if you're at a low temperature, the gas particles start to slow down. They start to form a liquid, which is the opposite of an ideal gas. A lot of students tend to prefer that explanation to the mathematical one, but choose the one that works better for you. Right, that is all for today's video. Thank you so much for watching and have a great night.